everyone, Miss Basega here, and I'm here to review with you for the Unit 12 Nuclear Physics test on Thursday. So what I'm going to do today is I'm going to go over our review practice test that we had on Tuesday, and what I'd like you to do as you follow along is grab a pen, pencil, whatever it is you write on or write with, doesn't matter to me. Maybe not crayon though. Grab the thing. And as we go forward, I want you to take note of the sections that are starting to come up and the skills under each section. Why? Because your test on Thursday is going to have the same sections and the same skills, just asked in a slightly different way. That way, if you can think of something on this that you don't quite understand how we get, you'll be able to go ask that question to your teacher, hopefully before Thursday's assessment. So let's get started. Class period, let's just say I'm period 1 and 2. Model 1, so please write this down. Representation of nuclides. The nucleus. For this, you should be able to determine based on the chart, or based on the representation, the atomic number, the mass number, number of neutrons, number of protons, and number of total nucleons. Now notice that this is just for the potassium-40. All right, the atomic number is 19. That's also the number of protons. But 40 is actually the number of total nucleons. That means of the 40 particles, if 19 are protons, that means 21 are neutrons. Now the 40 on top is both the mass number and the number of nucleons. What do they have in common? Well, let's see. They all have a mass number of 40. That means they have 40 total nucleons, and they're not going to have the same chemical properties because they're all different elements, right? Remember, your chemical properties come from your atomic number. They're not necessarily going to have the same nuclear properties either, right? So same number of nucleons. The nucleus is held together by the strong nuclear force. Ooh. Okay, so now we're talking about alpha, beta, and gamma emission. And I wrote this question as a throwback to when we originally did magnetic fields. But one way that we study nuclear particles is we can put a sample over here by A, B, C, and D. If it bends one way, it's positively charged. If it bends the other, it's negatively charged. So C must be a gamma particle because it goes straight. When comparing sample A to sample B, they both go in the same direction, which means they have the same type of charge. In fact, A and B are both positively charged. But this one requires a little bit of reading. Because more massive particles are harder to deflect, they have particles with a larger radius. So B must be more massive than A. They have the same sign of charge, but B is more massive than A. Most likely, when you're studying for your test on Thursday, you won't need to memorize anything about like this magnetic field stuff, this mass radius relationship, because it would be given for you in the stem of the problem if you need it. Right? Now, match the type of particle on the path. Alpha decay sample A and sample B are both positive, but A is heavier than B. Sample C is a gamma because notice that sample C is neutral, and sample D is negative, so that must be the beta minus. So the nuclear physics part of this section then is be able to tell apart alpha, beta, beta minus, and gamma decays based on the fact that alphas are heavier, betas have the same mass but one's positive and one negative, and gamma is neutral. Similarly, in this problem with Model 3, X, these like thick alpha particles must be the alphas because these are more charged. Notice that you don't have to know the charge relationship here. It says in the text, the more charge a particle has, the thicker the cloud is formed. you should know that an alpha particle has +2 charge, so it has more charge than either a plus or minus beta. A drawback is that, well, all of the above. We can't tell positive from negative in a cloud chamber. If you check out this cloud chamber, which is kind of cool, we can see that there are charged particles going through, but we can't tell how massive they are. We can only tell how charged they are, where alphas are the thicker clouds because they have more charge than betas. Now remember that because they have more charge, alphas are more dangerous to people. They're specifically dangerous if you inhale or ingest them. That's because normally the alphas would get stopped by your skin. But if it's already inside your body, like if you live in a basement and you breathe radon gas all the time, then that decays in your lungs, increasing your risk for cancer. Okay, so in this section, you should be able to tell apart alpha, beta, gamma radiation. You should also be able to do the equations for it. So this is radon. It's got to either be choice 3 or 4 because I need to see that it has an alpha particle, that's that 4,2 helium. But it's going to be option 4 because this has to transmutate from radon to a different element. And in this case, it transmutates into polonium, which also would stay in this person's lungs, right? And the polonium would also alpha decay. And all those alpha particles would all get emitted directly into your sensitive lung tissue. A person that's inhaled radiation has been contaminated. That radon is now in their body, right? Okay, so in the next section, section 3, we have radioactive decay. The one with, let me zoom in here. Remember that half-life is something that is the amount of time it takes to go from 100% to 50%. So the uranium half-life here is at 0.67 billion years. Well, that's faster than 95 billion years over here. That's faster than 46 billion years for rubidium, and that's faster than 1.23 billion years. So the uranium has the shortest half-life. You probably had to zoom in to find that. So if there are originally 10 grams of each of the 4 radioactive nuclides, which would you expect to have more parent nuclei remaining after 100 billion years? Notice the chart doesn't go up to 100 billion years for all of them. Well, in this case, at 100 billion years, keep in mind that uranium and potassium have shorter half-lives, so they will have decayed away entirely. At 100 billion years, samarium has something on the order of like 50% of its particles. At 100 billion years, the rubidium has something like 20% of its particles. So samarium would have the most parent nuclei because it has the longest half-life. The uranium and potassium have much shorter half-lives. And you'll see when you get the feedback from your questions later, you'll see that because they have much shorter half-lives, they'll have decayed away entirely after 100 billion years. But that leaves samarium and rubidium will still have a measurable amount left over. Now the half-life of rubidium-87 is 50 billion years. At 100 billion years then, you would start with 10, and it would get cut in half 2 times. Once at 50 billion years, so then you'd have 5, and once at 100 billion years, so then you'd have 2.5. For half-life then, you should be able to read half-life off a chart. You should be able to calculate how much is left over after a certain amount of time. And here, we should be able to figure out how half-life is related to the age of a material. So, woolly mammoths in this case, if the fossil of a woolly mammoth was found I would use none of these because we would need biological instead of mineral dating. Unless this woolly mammoth was eating uranium, it doesn't make sense to use any other form of dating except for carbon. Now, this wording's a little bit funky, so bear with me here. Carbon-14 is very, very rare in nature, but it exists in a predictable quantity for living objects. For every large amount of carbon-12 atoms, there's one that's carbon-14. So as that ratio dies, there would be fewer carbon-14s per the same number of carbon-12. Or the other way to say that is one carbon-14 nucleus to many more carbon-12 nuclei once the item has died. So notice our numbers here. Now the ratio is no longer 1 to 7.4, it's 1 to 14.8. That must mean one half-life has passed, or about 5,730 years ago. To radiometrically date how long ago the Stegosaurus walked the Earth, we could do this, and we could use this by dating the surrounding layer of rock to estimate the age of the Stegosaurus fossil. Okay, so question 17, if you get farther from a source, you get less radiation. This is actually an inverse squared relationship because that radiation spreads out over a larger distance. If you have a radioactive material in your backyard, do all of the above. Notice this is time. You spend time away from this. Distance, stay far away from the meteorite. And shielding, hide behind concrete. Time, distance, shielding. For alpha radiation, it doesn't matter what you use. Alpha radiation can get stopped by your skin. It's going to get stopped by aluminum, steel, and lead, all equally the same. But where it matters is gamma radiation. You want to put as many particles or as many nuclei in between you and the source. So for gamma radiation, a lead shield, which is denser, would be more effective than aluminum or steel. I had a lot of questions on half thickness. Half thickness is the amount of shielding you need to get rid of 50% of the radiation. So if you started with 160 counts per second, 80 counts per second occurs at 4 millimeters. That's your half thickness. Radiation exposure that provides the least exposure for the average person is actually from nuclear power plants. Cosmic, internal, and terrestrial are significantly more. Cancer from radiation? It's actually just these two. A lot of people think your cancer is worse if you have worse radiation, but that's not true because your cancer occurs statistically. So if you have cancer, it will be equally bad no matter how much radiation you receive. And since most average people are not being exposed to ridiculous amounts of radiation on a yearly basis, cancer is the most probable thing. You're probably not going to do things like lose your hair or your skin falls off or anything like that, right? But the more exposure you have, the more probable cancers are. So stay safe. Time, distance, shielding. Last section. In the last section, you should be able to tell apart fission, fusion, and name their uses. So this is a common fusion reaction, and I can tell because these are low atomic mass nuclei. There we go, I said it. Two small nuclei make a big nucleus. This requires very, very high temperatures because we need the particles to move fast enough to overcome this positive charge repulsion. The two nuclei are positive, so they repel each other. This reaction would most likely be formed in a young star because older stars, like in 28, do more complex reactions that go up to about oxygen. Ooh, I realized there are two correct answers here, so fixing 28 later. Right. Finally, 27. We would expect to see fusion in all of the above, in multi-stage thermonuclear weapons, or in fusion-based reactors. Now, I didn't talk about fission a lot in this section. Maybe that's a hint. But expect to be able to tell apart fission, fusion, and their uses. Okay? Best of luck, guys. Bye!